All right, here is a pretty standard Newton's second law for rotations kind of problem. Just have to be, I really have to say, at the end, this ends up being somewhat more involved than the College Board is likely to ask you to do. It's the algebra that goes on ends up being a little bit deeper than they want you to do. Not that it's beyond your abilities, but it's sort of beyond the level that they expect for intense problem solving. If this kind of problem excites you, it's exactly the kind of thing that the College Board asks you to do in AP Physics C. So feel free to take that class if you'd really like to dive into this. Nonetheless, I'd like to walk through this problem just so that to sort of tie a bow up on our rotational dynamics stuff. So we have a weight with some mass mw that's tied to a piece of thread wrapped around a spool, which is suspended in such a way that it can rotate freely. When the weight is released, it accelerates towards the floor as the thread unwinds. Assume that the spool can be treated as a uniform solid cylinder with given radius and mass, m sub s, and find the magnitude of the acceleration of the weight as it descends. Assume the thread has negligible mass and does not slip or stretch as it unwinds. And after that, we'll find the tension in the thread. So this is clearly some sort of dynamics problem. And so we'll need to do a free body diagram for the hanging weight. And then we'll also need to do some sort of dynamic analysis of the spool, which will be trickier for College Board type things because it's not going to quite fit the free body diagram the way that we usually do. All right. So the free body diagram of the descending weight is it has its own weight pulling down. That's mw times g. And it has some tension pulling up. I'm not trying to get these to the right scale, just the correct directions. And as a result of these two things, it accelerates downward, and I'm just going to call that A1. Meanwhile, over here we have the spool, and the spool suffers its own weight, acting at its center and pointing down. That's msg. And of course, the thread exerts a tension down on it, pulls down on it as well. That's Ft, the same Ft as the other one. And then also, there's some sort of axial force. There must be something coming from the axle on which the spool is sitting so that the whole spool doesn't just collapse to the ground. Right? That is at least potentially disturbing because we don't know anything about it. All we know is it's big enough to stop the spool from accelerating downward. The combination of all of these forces produce no linear motion, but they do produce an angular acceleration, alpha 1. We can start writing some equations. So we can say, let's do second law for the hanging weight, and that says that F net is MA, RA is A1, and if we look at our diagram, we'll take downward as our positive direction because that's the way A1 points. Then we have MWG minus the thread. And then there's no Newton's second law for the spool because it's assumed it doesn't slide or move anywhere. So all those forces balance out, so I could have them add up to 0, but that won't tell me anything because FA is completely unconstrained. On the other hand, there is the Newtonian equivalent, the rotational equivalent for Newton's second law, which tells us that tau net equals I alpha. Here we'll have to either remember or look up or somehow get a hold of the rotational inertia of a spool, but they said treat it as a uniform cylinder, and therefore you would be able to know, or on the AP you would be told, that it has an inertia which is 1/2 the mass of the spool times its radius squared. Sorry, that's a pretty bad R. The radius squared. All right, and again, you're not supposed to remember that offhand. That's a thing which you can know, which you can get from notes or from a textbook, or in this case, or on an exam that they would tell you. We can process the generic statement tau net equals I alpha now into another thing, which is that 1/2 msr squared times alpha 1 is the net torque, and that's going to be easy because there's only one force that exerts a torque. Fg, all right, MSG doesn't because it points through the rotational axis, and FA doesn't because it also points through the rotational axis, so they don't contribute to the torque. All we have is the tension, and the tension is perpendicular, it's tangential to the spool, so the moment arm is just the radius of the cylinder, which is remarkably convenient, so we get that it's just the tension times R. All right, let's get a feel for what we already know and don't know in this collection here. So I'll highlight in blue. We don't know the acceleration. We don't know the tension. We don't know the angular acceleration, and we don't know, again, the tension. We do know the masses, and of course we know g, and we know the radius. Those are all given. But we don't know the two accelerations or the tension. So it looks like we're in a little bit of trouble because we have only two equations and we have three variables. But it's actually not that bad because we do have one other connection. It's not a Newton's law. It's a kinematic connection. It connects the linear acceleration to the angular acceleration. The basic thought here is that if you consider the string, every point on the string here must be accelerating as fast as the weight. Right? The weight starts accelerating downward, and it must be that this has the same acceleration. If they had a lesser acceleration, the string would snap. If it had more acceleration, the string would bunch up, but we're told that neither of those things happen. All right? It's a smoothly unwinding string. On the other hand, the disk is rotating, the spool here is rotating, and so the points on the edge that where the string is have a rotation, and we know that there's some linear acceleration here that corresponds to the angular acceleration, and we might remember that that rotational acceleration fits the idea that the acceleration of any point tangent to a circle is the radius, the distance from the center, times the angular acceleration that it's undergoing. And the thread has to have that acceleration, has to match that acceleration. Because again, if the thread were accelerating at a rate different than the edge of the spool, then it would either bunch up or break. But that means we've connected that A1, the acceleration of the mass, has to be the same as the translational acceleration of a point on the edge of the spool. So we end up with that RA1 has to be the radius of the spool times alpha 1. And now we can see we've picked up no new variables, but we've picked up a new equation. We now have three equations and three unknowns. And so in principle, this is solvable. And before we go any further, let's pause there and just say that's sort of the level that they'd want you to know, although even here it's more to set up than they would probably expect you on the College Board to do. But it shouldn't be terrible, and this connection is important, that the acceleration, the linear acceleration of the weight has to be the same as the linear acceleration of the edge of the spool. Right? The rest of this is going to be algebra to go through, and it's certainly worth looking at if you want to check yourself, see that you can do the algebra, but it's not going to be a lot more physics anymore. It's just going to be doing some arithmetic or some algebra. So to recap, here are three Newton's law equations plus the kinematic equation we have. So here we have the second law in translation for the falling weight, and here we have the second law in rotation for the spinning spool, and then over here we have the connection between the acceleration of the falling rate and the angular acceleration of the spool. And on one level, it's just algebra, which doesn't comfort you very much, but we can do. And so I think I'm going to take the middle equation here, and I'm going to say, the first thing I'm going to say is that we can cancel an r, and so we're left with, when I do that, this equation becomes 1/2 ms r alpha 1 equals ft. And that's convenient because that's already given us something in terms of the tensions. And then we're going to take this stuff and plug it in. So we're going to say that, notice, R alpha 1, we already have that, and so we end up with 1/2 ms A1 equals ft. And that's very convenient because then I can go and take that and plug it in up here. So now I have mw times A1 equals mw times g minus, and I can make that 1/2 ms A1. From here on, it really is simple single variable algebra. I bring this over to the other side. So I have mw A1 plus 1/2 ms A1, and all of that equals mw times g. And we can factor out the A1s and divide, and we end up with that A1 is going to be mw times g over mw plus 1/2 ms. All right, plugging in their numbers for that. For instance, for my version of the problem, mw was 150 grams, which is 0.15 kilograms. And g, of course, is 9.8 meters per second square. And ms was 200 grams, so it's 1/2 of 0.200 kilograms. And let's run that in a calculator. And I get 5.88 meters per second square, which agrees mostly with sapling. We seem to disagree a little bit on the last digit because I probably rounded in a place they didn't, or vice versa. And then the second part says find the tension, but that's pretty easy because notice that we already have an expression for the tension. So we can just say, oh, the tension is 1/2 times the mass, which was 0.200 kilograms, times that acceleration, 5.88 meters per second square, and we get 0.588 newtons, and again agreeing to the same amount with sapling as before, just because of some rounding issue that I don't feel like tracking out. So there we go. The last part being almost obnoxious once you've done the rest. And this is still, I mean, intense, but not overwhelming, would be my argument on that.